Regarding what the topic we covered last night, one of you was asking me a question regarding the limit of the integration here. Like over here, we integrate y from uh, minus of square root of 4 minus x squared to plus of square root of 4 minus x squared. However, we integrate x from minus 2 to plus 2. The question was, why are we not taking the limit of y from minus 2 to plus 2? So the question is, why are we not taking the limit of y from minus 2 to plus 2? Okay, so here the intention is to integrate over the whole volume here, to integrate over the whole volume of the cylinder. Let me draw the cylinder here. Okay, so I'll try to make the best cylinder as I can draw with my stylus pen here. So let's say you have a cylinder here. This is your x, y, z coordinates, and you have a cylinder like this. Cylinder like this, and the bottom of the cylinder is having an equation z equal to 0, because for every point on the bottom that is like a perfectly plane on the xy plane, for all the points on this circular bottom here, z value is 0, and for all the points on the circular top here, z value is 3. So we have to perform volume integration of divergence of the vector A. There we have to take d tau. And as I said, when we consider this Cartesian system, our d tau is something like a small volume element. Small volume element. D tau is small volume element consisting of increment along x, that is dx, increment along infinitesimal increment along y, infinitesimal increment along z, dx, dy, dz, that will form a small cubical volume. So this is your dx, dy, dz. So this is a small like volume element. And in order to cover the whole volume here, so when we are integrating this quantity, our objective is to sum, say, we are estimating divergence of A. When we write divergence of A into d tau, what this gives us is that we are estimating the divergence of A within this volume d tau. So divergence of A into d tau will simply give us an estimate of divergence of A within this volume element, divergence of A within this volume element. So this will give us an estimate of the net outflow of the vector A within this volume element. Now, when we are performing volume integration, we have to sum over the whole volume which is within this cylinder. So our first objective is to sum along the z-axis. So if we sum like this, that is, assume that there is another infinitesimal small volume, there is another infinitesimal small volume, infinitesimal small volume like that. So there is an infinitesimal full volume, so infinitesimal small volume here at z equal to 0, and z equal to certain value also, there can be certain infinitesimally small volume like this. So you can have plenty of infinitesimally small volume element here. And by taking the limit of z in this integration from z equal to 0 to 3, what we do is we are summing from this to this. So we will have some sort of rectangular rod after performing the integration with respect to z here. So this is something we integrate. First, you perform the integration with respect to z from z equal to 0 to 3. That is, we are summing up whatever we are doing, that is divergence of A from the bottom to top here, right? So our next objective is to move this rectangular rod like around this circle so as to cover the whole volume here. So if I choose the limit of y from, let's say here we know that the radius of this circle is, the radius of this cylinder is 2, because the equation of the cylinder or the equation of the circle is x square plus y square is equal to 4. So r square is 4 means r is 2. So if I take the limit of y from -2 to +2, if I take the limit of y from -2 to +2, what this will execute is that if I integrate y from -2 to +2, what it will execute is that after performing the integration with respect to z, if you integrate from -2 to +2, it will simply take this rod from, let's say this is -2, this rod it will take from -2 to, it will move up to, this is, let's say this is +2, it will move along this line. So after integrating with respect to y from -2 to +2, what we will be having is something like this. What we will be having is something like this. This is what we will be having after integrating from, this is, let's say -2, let's say this is +2. So this is your origin. So you will have a rectangular block now if you take the limit of y from -2 to +2 with respect to y. Now after this, if you perform the integration of x from -2 to +2 again, perform the integration of x from -2 to +2 again, so you see that this is your x-axis. So there is +2 here, there is a -2 there. So after this, if you perform this summation again, so you can assume that there is a rectangular block at x equal to -2, and there is another rectangular block at x equal to +2. So you will sum up from all, you will do the summation of all these rectangular block from -2 to +2. Then what will be the result of this integration? The result of this integration will cover, something like this. It will cover a rectangular it will cover a rectangular block like this. The result of this integration will be covering this whole volume, isn't it? So this is what we will achieve if you take the limit of z from -0 to +3 and limit of y from -2 to +2, limit of x from -2 to +2. This is what we will achieve. So we will not be integrating over the volume enclosed by the cylinder. We will be integrating over the volume enclosed by this rectangular block. Our final estimated value of the volume integration will be wrong. When we are supposed to integrate over a cylinder like this, if you take the limit like this from y from -2 to +2, x from -2 to +2, you will instead have integration over this rectangular block. Okay, so that is the reason why when we have a problem like this, x, y, and cylinder, to integrate over this cylinder, first thing is by choosing z limit from 0 to 3, we have achieved this rectangular rod. Now, instead of taking this rectangular growth from -2 to +2 and if we take from -2 to +2, we realize that we will have this kind of rectangular block. And if we take the limit from minus x equal to -2 to +2 again, then we achieve this kind of rectangular block, right? So in order to avoid such result, the limit of x and y has to be chosen very carefully so as to integrate over only within the volume of this. So for that, what we take is that we know that the equation of this circle is x squared plus y squared is equal to 4. Then we choose our y limit as y equal to minus of 4 minus x squared to y of plus of 4 minus x squared. So only when I choose the limit like this, the integration limit will be defined by the equation of this circle. The integration limit is now defined by, or the integration limit is given a certain constraint, a certain condition by the equation of this circle, right? So this equation of this circle gives the integration limit, or it gives a constraint so as you will move this rectangular rod within this circle. You will move this rectangular rod from within this circle, right? So after you choose this, if you again choose your x limit from -2 to +2, then only you will be able to cover the whole volume within this cylinder. So the step of this integration from y to this minus of square root of 4 minus x squared plus of square root of 4 minus x squared, and integration from x equal to -2 to +2 is to move this rectangular rod within this. So by moving this rectangular rod within this cylinder, it will cover the whole volume. Okay, so that's the only way I can explain this. Now I hope that gives you satisfaction, because you certainly know that if you choose the limit like this, you will not arrive at that cylindrical volume. Okay, now this is another theorem. So this is also another three-dimensional theorem. It says that if S is an open two-sided surface, in the Gauss theorem, here, Gauss divergence theorem, we have closed surface. We have closed surface. It could be a sphere. It could be anything but a closed surface. We are dealing with a closed surface, enclosing a closed surface, enclosing a certain volume. It could be a surface something like this, but it encloses a volume. So a closed surface enclosing a certain volume is what we discuss in Gauss theorem. We have if we have a physical problem that deals with a certain enclosure, a certain closed surface which encloses a volume, then we have to employ Gauss theorem. And the condition was that it should be a simple closed surface. There should not be like some pockets like this, right? Now here, now when we get into Stokes theorem deals with an open surface. Stokes theorem deals with open surface. Yeah. So open surface means it does not enclose any volume. Does not enclose any volume. Open surface means does not enclose any volume. Like, for example, if you consider a cone like this, cone. If you consider a cone, as you know it, it's an open surface, isn't it? So you have a boundary here at the bottom, a circular boundary at the bottom, and you have a conical surface. You have a conical surface, but this is not a closed surface because the bottom side is open and this cone is somewhat empty here. If you consider an empty cone here, it is an open surface, right? And also you can consider like semisphere. Like if you cut a sphere into, if you have a hollow sphere, and if you cut the hollow sphere into half, if you cut the hollow sphere into half, you will have a certain open surface like this. If you cut a hollow sphere into half, you will have an open surface bounded by a curve. There is a curve here. There's a curve here bounding the open surface. A curve bounding, or a curve formed by a curve which is bounding an open surface, right? We will be dealing with an open surface bounded by a simple closed curve. So what do we mean by a simple closed curve? Simple closed curve means there is no intersection of the curve like this. This is not a simple closed curve. Okay, closed curve means those curve which has no intersection in itself, right? And the direction of the closed curve is always taken in an anti-clockwise direction. This is an anti-clockwise direction. See, this is a clock. Clockwise direction means the clock is moving in this direction, right? So anti-clockwise direction is this. So whenever we are considering a closed curve, if we move in anti-clockwise direction, that is considered as the positive direction. In any vector integration, positive direction of integration in a simple closed curve is taken as anti-clockwise direction. So here, if I have an open two-sided surface bounded by a closed non-intersecting curve, that is what we mean by a closed non-intersecting curve, and if A has a continuous derivative within such surface, then Stokes theorem says that line integration of your vector function throughout the closed curve equals surface integration of curl of the vector field. Okay, so here C is traverse in a positive direction, means again whatever closed curve you are taking, it is in the positive direction. Okay, it is in the positive direction. It could be, as I said, something like this. Maybe like you are this thing, Santa Claus cap also, something like this. You can have a surface, but an open surface. So you have a top surface, you have a bottom surface, because considering that this cap is hollow and it is surrounded by a closed curve, C here, which is traversing in a positive direction, counterclockwise direction. Okay, then in such case, when you take the vector line integration of this vector field in an anti-clockwise direction, that equals curl, surface integration of curl of the vector field. Okay, now this is a tutorial just to clarify, or just to give you as an example here. So the question here is verify Stokes theorem for A vector is equal to this, where S is the upper half of the sphere. S is the upper half of the sphere. That means you have a hollow sphere like this. You cut the sphere into half, and this is called the upper half of the sphere, upper half of the hollow sphere. So this surface S has two sides. One side is the top of the sphere. One side is the inner side of the hollow sphere. One side is the outer side of the hollow sphere. Another side is the inner side of the hollow sphere. So it has two true surface, right? Open surface will always have true surface. And the equation of this sphere, the half surface of the sphere, is x squared plus y squared plus z squared equal to 1. That means we know that the equation, the general equation of a sphere is x squared plus y squared plus z squared equal to a squared, where a is the radius, or you can write r squared also, if the center is at 0, 0, 0, right? So I think you already know the equation of a sphere. If the center is at another point, then x minus 1 whole square plus y minus 2 whole square plus z minus 2 whole square equal to a square. So if the center is located at 1, 2, 2, 1, 2, 2 coordinates, if you have the center of the sphere at 1, 2, 2 coordinates, this will be the equation of the sphere. But when the center of the sphere is at the origin, that is 0, 0, this is the equation of the sphere. So the radius of the sphere here is 1 only, right? So now, considering what I have just explained, you see that the boundary of this open surface, the open surface is the upper half of the sphere, will be a circle of radius 1 on the xy plane. See, there is a on this xy plane, there is a circle here. This circle will be the boundary of this open surface we consider for this particular problem. Okay, so your C here, your closed curve here is a circle of radius 1. So on the xy plane, you have a circle of radius 1, means on the xy plane, z value is 0. The equation of the circle on the xy plane will have to be x squared plus y squared equal to 1. This gives us an equation of a circle on the xy plane. Right. Now, we know that here we have to perform line integration of the vector around the closed curve. So in order to perform line integration, we have to define what is called line element. Line element. So you know that the general expression of the position vector in xyz coordinate system is xi plus yj plus cap plus zk cap. Then the line element dr vector will be simply writing dr vector is equal to dxi dyj plus dzk. Okay, simply we can write a line element like this. Then you can take a dot dr, because here we have to perform your a dot dr here, then integrate over the closed curve. A dot dr, you have your a vector here, and take a dot product with your dr. So I dot I is 1, j dot j is 1, k dot k is 1. If you follow the vector notation that I, j, and k are orthogonal unit vectors, then this is what you arrive at. Okay. But we know that in order to perform this loop integration of your a dot dr, as in the Stokes theorem, in order to perform this loop integration of your a dot dr over the closed curve C here, you know that for every point on the closed curve C, as in this particular problem, z value is always 0. Why is z value always 0? When you integrate over this closed curve, that is by moving around this closed curve here, for every point here, z value is 0, because the closed curve, which is a circle on the xy plane, is x squared plus y squared equal to 1. Here, z value is always 0, because we have a circle on the xy plane. Z value is always 0. So by putting z equal to 0 here, eventually you will have a dot dr as 2x minus y dx. Okay. Now our objective is to perform loop integration over this circle on the xy plane. This is x-axis, this is your y-axis. So this circle will be the loop, the closed curve bounding your open surface. So in order to perform